Welcome from Berlin to our webinar on the future cost of electricity-based synthetic fuels. We're glad to have more than 70 participants online now, and this webinar is based on our joint study by Agora Energiewende and Agora Verkehrswende that we published in April. And this study was published to create more transparency in future discussions on synthetic fuels, and therefore we have commissioned the consulting firm Frontier Economics to analyze cost reduction paths for synthetic fuels and investigate favorable locations in Germany and abroad for generating the renewable power needed to produce those fuels. Building on this cost analysis, then we have drawn our own conclusions, in which we discuss priority fields of application of synthetic fuels, necessary conditions to unlock the projected cost reductions, as well as the need for an adequate policy framework, which includes sustainability requirements for synthetic fuels. So, who are we? My name is Matthias Deutsch. I'm a senior associate with Agora Energiewende in Berlin.
And I'm Maier, a senior associate with Agora Verkehrswende, or Transport Transformation.
Our presentation today will last about 25 to 30 minutes. Before we begin, allow me a few words on technical stuff and how you can contribute to the discussion later on. All information related to this webinar can be found on our websites. This includes our study on the future cost of electricity-based synthetic fuels, an interactive Excel spreadsheet cost calculator to adjust the underlying assumptions for the cost analysis. You can also download the webinar presentation and the webinar recording, which is also available through a YouTube channel. You can already now download the presentation slides from the webinar software, and a pointer should appear now on your screen indicating where you can download it. And also now a little chat window should appear on your screen that you can use to send us real-time questions on the presentation. We will address these questions in the question and answer session after we have gone through the presentation first. If you pose a question, this question will only appear on our screens. The other webinar participants will not see it. So when replying, we will restate the question first and then try to answer it. It would be kind if you were to mention your name and affiliation when asking a question. We'll try to cover as many questions as possible during the question and answer session. Remaining questions we'll take up by email afterwards. You can also use the chat window to submit technical questions or remarks in case you are experiencing problems with the software. Our colleague Nicola Bock, who is sitting next to me, will seek to help as fast and as far as possible. So thanks, Nicola, and also thanks to our colleague Christoph, who is working behind the scenes and keeps the system running technology-wise. So, well, that's it for the introduction. Let's get started. And so when we go to the questions later on, I will pass on the questions, and at around 5 to 5 p.m. we'll stop questions and answers, and then Urs will take over for closure. Well, let's get started then.
Yeah, thank you. Hello and warm welcome from my side as well. When we started this project, there were many climate protection scenarios out there showing a huge demand, or a demand at least, for synthetic fuels, especially for the time period 2030 to 2050. That's why we commissioned Frontier Economics to analyze the cost path, as Matthias already said, to get a better idea of what role those fuels might play, should play, could play in future, and the energy transition. So what we are doing today is we're gonna present you our conclusions of the work of Frontier Economics, and those are basically 4 main conclusions. But before I start with the first conclusion, I want to say a few more words on our think tanks we work for. We are sharing an office, Agora Energiewende and Agora Verkehrswende. We are about 40 experts, independent and non-partisan. That's because we are financed by 2 foundations, the Stiftung Mercator and the European Climate Foundation. Agora Energiewende started a bit earlier in 2012. Their current phase is financed until 2021, and Agora Verkehrswende, as we see it, the little sister, we started in 2016, and we are financed until 2023 so far. Our common mission is to develop strategies to decarbonize the energy system in Germany and beyond. Our focus is on power, heating, and transport. And what we do is we do analysis ourselves. We commission studies. We offer a marketplace and a forum or an Agora for debate for different social groups. And what helps a lot is that we have councils of the Agoras that we can consult with. And they consist of high-ranked representatives of politics, companies, science, and civil society. So that's a few words on who we are. And before we go into the main part of the presentation, I want to show you what we're actually talking about. And those are the electricity-based synthetic fuels, power to gas and power to liquid. So you start at having electricity from renewable energy on your left-hand side. It's very efficient to use that directly, but sometimes you want to store that electricity and over a longer period of time, or any restrictions you can think of. So you can split water with the help of electricity into hydrogen and oxygen. You get an energy carrier that has the advantage that it doesn't include any CO2, so there's no CO2 emissions when you use it. But a disadvantage first, that you have conversion losses creating hydrogen, and also that you have an infrastructure and applications hardly in place, or quite expensive so far at least. So what you want to do when you have applications where you can't use electricity directly, it's too expensive, thinking of maritime transport or aviation, then you can add CO2 and through the processes of methanation or Fischer-Tropsch or the methanol route, you can get power to gas, synthetic methane, that's methanation, which can be used like compressed natural gas or liquefied natural gas, or you can have liquid fuels, power to liquid, gasoline, diesel, kerosene. The reason why we put it into those pink, why we highlighted those two terms is to show you that if we don't state otherwise, with power to gas and power to liquid, we mean those electricity-based CO2 based fuels. Hydrogen certainly is also power to gas, but with our study we focus on the CO2 based fuels. So let's say a few words about the study. It is commissioned by our two think tanks, Agora Verkehrswende and Agora Energiewende. Frontier Economics did the work. The guiding questions were: how can the cost of importing synthetic fuels, that is methane and liquid fuels, develop until 2050? With an exemplary analysis for North Africa, for Middle East, and for Iceland. And the second question, to compare that to the German context, was: what are the costs of producing those fuels on the basis of offshore wind energy in the North and Baltic Seas? The approach, a cost estimation along the value chain, so power generation, conversion, transport, blending / distribution. The cost ranges Frontier get from the literature and also from an expert workshop that took place here at the Agoras. And it's important to mention that CO2 neutrality was, we got that by assuming CO2 from the air, so direct air capture. Let's start with our first key conclusion out of 4. Synthetic fuels will play an important role in decarbonizing the chemical sector, the industrial sector, and parts of the transport sector. And we should have a look at how oil and gas are used today. And this shows the use in Germany in 2015 in terawatt hours. You can see that oil and gas are of crucial importance for Germany. You see that oil is used mainly in transport, but also in industry for non-energy use, in heating, and very little in power generation, and that gas is predominantly used for heating, and a little bit, of course, and of high importance as well for power generation and combined heat and power plants. You can see on the right-hand side that the energy mix in Germany in 2017 was more than 50% dependent on fossil oil and gas. So if we look at the situation right now, and we see that against the Paris Agreement, against the background of the Paris Agreement, the German climate protection goals, and other countries' climate goals, can we substitute those fuels on a one-to-one basis with the electricity-based synthetic fuels we just introduced? We think no, and that is mainly because of the conversion losses, because of high efficiency losses you get from producing those fuels. So what we did, we brought you 2 examples to visualize those conversion losses, and I'll start with the one on transport. You can see here individual and overall efficiencies for cars with different vehicle drive technologies in a comparison. On your left-hand side, you see the battery electric vehicle, and what you can see is that if you put in 100% renewable power, you get 69% to use it to get from A to B. If you go for a fuel cell vehicle using hydrogen, then you need 2.5 times more electricity to get the same distance traveled. In the end, it's only 26%. And if you then look at the internal combustion engine vehicle, you see that you need 5 times more electricity than for the battery electric vehicle. Mainly because of the conversion losses, but also, and this is important to mention, because of the lower efficiency of the internal combustion engine vehicle in comparison to the electric motor. So far as to the transport example.
So let's also have a look at heating, the heating sector. And by the way, we didn't come up with those figures by ourselves. We just basically drew them from the German National Academy of Engineering that published something in the last fall, and we drew most of the figures from them. So we think that's a pretty robust understanding of what the conversion losses are. But let's look at the heating sector. Now, for the heating sector, you have the electric heat pump, fuel cell heating, and gas condensing boilers in those 3 rows. And when we look at fuel cell and gas condensing boiler first, you realize, starting with renewable power, 100%, you end up with about roughly 50% in each case. And let's not argue about a percentage point more or less here or there. Because as I said, again, most figures are from the German National Academy of Engineering. Yes, things may change in the future a little bit, but by and large, the importance here is that when you now look to the left column, electric heat pump, you basically used your renewable power to pump it up, so to speak, and with an annual coefficient of performance of 3, you end up with, in this case, like nearly 3 times as much energy that you can use for heating as you have put in as renewable power. And that is because we can use ambient energy from the environment, that is from the air, from soil or water, and then add that to the renewable power and use this entire energy more or less. And the comparison is simple. If you compare the 50% in the middle and to the right to the 285% there, you get the idea that what it means to have high conversion losses for synthetic fuels. Now, the open question, of course, is those figures that we just presented for transport and for heating are pretty much physics-based and more or less indisputable in that sense. So, can those indisputable disadvantages of synthetic fuels be offset or more than offset by some kind of advantages, for example, by avoidance of infrastructure cost? That's an open question. Our understanding, there's not that much research out there, and there's a need for better research, a better understanding, for example, better understanding the gas infrastructure system and under which conditions and where and maybe in what time frame there could be those advantages that can more than offset those obvious disadvantages. Now, what we have done is we have kind of tried to systematically put all sectors together in a big table that you can find in our publication. And now we go back to transport, which is kind of the first line in this big table of sectors, to see what a meaningful priority would be to think about using renewable power.
Yeah, and here you can see the transport example. In the first column you see there's a first priority direct use of electricity, and we put together some means of transport. And we also have in the third and fourth row column hydrogen and CO2 based power to gas and power to liquid as supplemental approaches as synthetic fuels. So the key messages you can find on your right-hand side. For road transport, the direct use of electricity should have priority. Long-haul trucks and buses will possibly use power to gas and power to liquid, although it is more efficient in terms of energy use to go for overhead catenary overhead contact line trucks or battery powered trucks, and of course it's always good to say that to shift from road to rail. So if you but if you want to go for power to gas, then hydrogen is more efficient than CO2 based power to gas or power to liquid and should therefore have priority. Power to gas and power to liquid will indisputably be employed in the air and sea transport. There it is it can't be foreseen today that it will be possible to travel by plane from Europe to Australia just on batteries. Those planes have a long lifespan, so we certainly will need drop-in fuels for air and sea transport.
And so let's have a look again at heating, building on what we already said. Now, for building heat, the direct use of renewables, and that includes deep geothermal, solar thermal, and that should have priority together with electricity. That means heat pumps for sufficiently insulated buildings. Now, that's critical, of course, and were useful also in combination with heat grids. Now, when you get to those insulation restrictions, then maybe fuel cell combined heat and power with hydrogen or CO2-based power to gas, power to liquid is a supplemental option that we should look at. This is low temperature. When we look at high temperature heat as process heat in industry, again, the direct use of electricity should have priority. We should really carefully look at other options. There's a lot of interesting physical processes out there. There's not only resistance heating, there's also infrared heating, some kind of plasma heating, different forms that we should look at before simply switching to the default that we are used to, which is burning stuff. So in the past we have burned fossil fuels, and here if we can't go any further, then maybe we will need power to gas, power to liquid for getting high temperature heat as well. There are two other things that we needed to look at, which is industry in the broad sense, including chemical industry. Now obviously if you need certain molecules, then you cannot just use electricity. So if you have some kind of inorganic chemistry that you want to deal with, then maybe you need hydrogen first, which could be the basis for ammonia production, or you could produce steel with direct reduction of iron ore. And if you go to the organic chemistry, of course you need some kind of organic basic chemicals, and there it makes sense to produce synthetic fuels that are CO2 based, and then you can derive other chemicals from that basis. Now the last thing we want to mention is something that has been up to debate, but I think now it's the least critical problem here when we talk about the power sector, because obviously for the short-term storage, like say storing electricity for a day or so, batteries are a priority in our understanding. So the question is, what do I do if I have long-term storage problems, maybe seasonal storage? There you need a chemical energy carrier, and so what you will do is produce hydrogen and probably also CO2-based power to gas, and then store that and then reconvert it in gas-fired power plants for those times where there's low feed-in from wind and low feed-in from solar, which is known in Germany as Dunkelflaute. So certainly power to gas will have a role to play in the power sector for long-term storage, at least when we get closer to very deep decarbonization scenarios of minus 95% or so. So this is what we have talked about so far, is the demand side. What is the possible demand for power to gas, power to liquid? Now let's look at the supply side. And there's an interesting discussion going on in Germany for a long time. When you ask people, so how do you want to produce those power to gas, power to fuels? And some answer, well, we basically use cheap excess renewable electricity. Okay, so starting from that, let's have a look at what we conclude in terms of what is the basis of producing power to gas, power to liquid. Our second conclusion is, to be economically efficient, power to gas and power to liquid facilities require inexpensive renewable electricity and high full load hours, that is, high capacity utilization. Excess renewable power will not be enough to cover the power demands of synthetic fuel production. And that is, the question is, how can you operate an electrolyzer, which is kind of the core technology, operate an electrolyzer to make it profitable, to make it competitive? And the literature says you would need at least 3,000 to 4,000 hours per year. I mean, if you can, run it all year long, but that's usually not an option. So 3,000 to 4,000 hours, can you find a source of energy with cheap renewable electricity supply for 3,000 to 4,000 hours? Let's have a look at that. And what you can see in the upper part of this diagram, and you can see hours per year, and in the upper part we see excess power for Germany, and there are some projections again by the German National Academy of Engineering, some simulation runs, how many hours of excess power, renewable electricity excess power, we can expect for the next 10 to 15 years to come. And what you see is in the next 10 to 15 years this excess power reaches around 1,500 hours per year at maximum. Well, then some people say, well, maybe it's not that we have this excess power in the whole German electricity system. Maybe it's just a regional thing. Maybe it's because of regional and local grid bottlenecks. So there's another study by some researchers that have looked at the northern region, the northern state of Schleswig-Holstein, north of Germany. And they have pretty aggressive onshore wind expansion plans. Now, if they fulfill their offshore expansion plans of the government in Schleswig-Holstein until 2025, they could reach a maximum of around 1,600 hours of excess, of kind of regional excess power, so to speak. Well, both figures for the whole of Germany and for Schleswig-Holstein is not really reaching the 3,000 to 4,000 hours you would like to have to run an electrolyzer economically. And by the way, for Schleswig-Holstein, there's an additional fact that's critical. Once the transmission system has been expanded in Germany, then the local grid bottleneck will disappear. That means that At first, you may have local grid bottlenecks and you may have excess power, but once the transmission lines have been built, maybe with some years of delay, then all this excess power in that region will then disappear, and that cannot be a basis for 4,000, maybe 4,000 to 5,000 hours. That's critical, and that is exactly what Frontier has done in the calculation of the synthetic fuel cost that I'll. So you'll see full cost of renewable energy facilities, you'll see version plants with electrolyzers, and you'll have, as my colleague mentioned at the beginning, CO2 from the air with direct air capture, all factored and priced in to reach those cost estimates of the future. So now let's look at the cost. And I'm on the next slide with our third conclusion. Our third conclusion will come up in a second. Sorry, this is again a technical challenge. So what you can see now is that our third conclusion is that in the beginning, synthetic methane and oil will cost between 20 and 30 cents per kilowatt hour in Europe, and costs can fall to 10 cents per kilowatt hour by 2050 if, and that's a big if by the way, if global power to gas and power to liquid capacity reaches around 100 gigawatts. Now, what you will see on the next slide is you'll see large cost ranges, which is our summary of Frontier's results. You'll see large cost ranges with a reference cost in the middle, and we in that diagram we also mixed gas and liquid just to have a big summary with big broad lines of thinking that emerges from this graphic. And so we'll now go to the next slide, and the next slide shows you a big summary of results. Let's start with the y-axis. The y-axis shows cent per kilowatt hour, and let's then look at the blue cost ranges. Blue represents offshore wind production in the North and Baltic Seas, and you see that in the early 20s it goes from 24 cent per kilowatt hour, that's what we call the reference cost. It goes down to around 20 cents by 2030 and around, let's say, 13 to 15 cents by 2050. That's the blue cost ranges. When you look at the very bottom of the diagram, you see fossil prices, fossil cost as a comparison. Those are cost projections from the IEA and the World Bank. It's a mix. And you see that they go slightly up, but at the core, the synthetic fuels produced with offshore wind will always be more expensive than fossil fuels. Now look at the pink color. The pink color represents PV and PV wind systems that are producing synthetic fuels in North Africa and in the Middle East. The basic idea is pink is less expensive than blue, so it is cheaper to import from the southern Mediterranean than to produce them with offshore wind at home. And then finally there's this greenish color that is the lowest. As I said, it's a mix of geothermal and hydropower in Iceland. The point here is that you can't beat that cost-wise, not as easily. But there's only a total potential limited to around 50 terawatt hours per year that we could get from Iceland. So this is an interesting option, but it will not solve Europe's or Germany's demand for synthetic fuels in total. So it's a good comparison, but it's not the entire solution to everything. So what do we learn from this? As I said, first of all, imports are cheaper according to those cost estimates. And there may be even further cost reductions coming up, something that could not be factored in by Frontier Economics. Maybe PV might be even have more aggressive and faster cost reductions, or maybe batteries may join the entire game, and that could be in favor of the import option if you combine even cheaper PV, maybe even someday with batteries in the southern Mediterranean, or you could construct very large chemical factories and plants and reduce cost even further. That's one aspect. The other aspect is that, well, you still need cost of capital. And here, Frontier Economics has assumed a general cost of capital of 6% for all options. Well, some of the North Africa, Middle East states may be a bit more risky for investors, and therefore cost of capital may be higher than 6%. So maybe the question of risky states and risky countries where you want to produce the fuel increases the overall cost, so that in the end, at least in the middle to long term, it's not that clear that the import option will always be more or will always be cheaper than producing at home with offshore wind. And finally, this is all about cost. So it's cost at the German border. But what about royalties? Some people have told me that it's not obvious that if you want to, put it simply, put a chemical plant somewhere into the desert, that you can do that for free. You will have to pay royalties in all likelihood. And also there will be most likely a global power to gas, power to liquid market that will develop in the future. And then we're talking about market prices, which are likely to be higher than the cost that you can see here. So all in all, we see cost reductions, and the final thought on this picture is, will those cost reductions come by themselves, or is there a necessary requirement? Well, the necessary condition is what we see at the next slide. The necessary condition is a major scale up. We know that. Remember PV came to major cost reductions by scaling up PV on this planet tremendously, first in Germany and some other countries and then in China. And the same question here is, how can we go through the cost learning curve of electrolyzers? And we think that those cost reductions require considerable early and continuous investments into electrolyzers. And that is an international challenge. And when you look at those learning curves, you can come to the conclusion that you need something in the order of 100 gigawatts to reduce cost, as Frontier has assessed those cost reductions. Compare that to the global stock today. We have around 20 gigawatts in the chemical industry installed electrolyzers. That is mostly alkaline electrolyzers. That's what the literature says. And so getting from 20 to 100 is quite something. And there are some other uncertainties when it comes to cost. For example, the technology of direct air capture for assuring climate neutrality is less mature than most of the rest of this technology here, and so it's unclear how easily we can reduce cost there. The key idea from the last slide is, well, as long as fossils are so inexpensive, then we need either high CO2 prices to have more synthetic fuels coming up, because by themselves they will not show up in the market. They cannot compete yet with fossil fuels, or you need some other kind of political intervention. So this is both important. And let me add one more thing here. Well, on the left side of this diagram you can see some German climate scenarios. I'll not go into details here, but the simple idea is that there are some scenarios out there for Germany by different institutions that foresee a lot of electrolysis in Germany alone. But the question here really is, can Germany alone bring down the cost to reach those competitive cost levels? And one final thought, and then I'm kind of done with the technical part of this analysis. One word on hydrogen. Hydrogen was not the core of our study, but still it's worth reflecting that hydrogen cost, just the production cost, is about half of the one of methane, as you can see in the diagram to the left. So it makes sense to think about hydrogen, especially since you don't need CO2 to produce it, and it doesn't emit CO2. So let's keep thinking creatively about where you can use hydrogen. The big advantage is no CO2 involved, so no need for direct air capture. The big disadvantage is that we cannot simply use existing infrastructure, and we cannot simply use the end-use applications. And with that, I'm handing over to Urs. So from my side, you have heard something about cost reductions, about a necessary massive scale-up of electrolyzers, of massive investments that we need, and maybe some infrastructure considerations. But I've also said we need political intervention. Now let's think about this political intervention.
Yeah, hello, and this is me again, and we are having the next slide in a second. Yeah. The fourth key conclusion: we need a political consensus on the future of oil and gas that commits to the phase-out of fossil fuels, prioritizes efficient replacement technologies, introduces sustainability regulations, and creates incentives for synthetic fuel production. To visualize that fourth key conclusion, we put together the following slide. And I need Christoph's help again. Okay, so what you can see here are the building blocks for an oil and gas consensus as we see it. At the beginning you have, or the start, for so to say, are the greenhouse gas emission reduction goals, and you then need an agreement on oil and gas consensus between politics, economy, and civil society. Three building blocks. First, phase out of fossil fuels, of fossil oil and gas. The new thing can't come if the old one doesn't leave. So we need a gradual decrease in the total use and associated emissions. We need, as a second block, a priority for efficient replacement technologies. For example, with battery electric mobility and electric heat pumps. So it's not a one-to-one substitution, as I said at the beginning, when we looked at the use of oil and gas in Germany. And the third block, incentives for synthetic fuel production on the basis of sustainability standards for power to gas and power to liquid, and application-specific targets. What does that mean? I have one more slide on sustainability standards, but on using an example for cars, I wanna make it a bit clearer. For cars, there is there's one directive in place by the European Union on CO2 from cars, the CO2 in fleet legislation. Cars need to get more efficient. The CO2 per kilometer in gram CO2 should be reduced. There are strict targets, and this increases the efficiency from a tank to wheel perspective. So this is priority for efficient replacement technologies. Battery electric vehicles have an advantage here. And then incentives for synthetic fuel production. This should be on the fuel side, on the emission factor side. If you want to have power to gas, power to liquid, if you would want to have that in cars, then you would go for the Renewable Energy Directive that decreases the emission factor of fuels, of liquid fuels. So it is not a good idea to look at the CO2 from cars legislation and to integrate power to gas, power to liquid there, but to keep that separated, tank to wheel and well to tank legislation. So application specific means we want to have a priority for the use of power to gas, power to liquid in maritime transport and in aviation, and certainly not as a priority option for cars. Let's have a look on the slide on the sustainability standards. We have 5. The first one is minimum greenhouse gas reduction, and we think that the entire production chain of synthetic fuels should lead to only to 70% reduction in comparison to conventional fossil fuels. This is what the European Union, with their Renewable Energy Directive 2, is going to say about advanced biofuels. So it's important to have that standard, because when you look at
the conversion losses, you must see that the emission factor needs to be multiplied by 1.9 if you want to go for power to liquid. So even with power to gas on the basis of PV energy, you only have a reduction of 80%, because PV production of electricity also has got a emission factor. So the second and the third one are kind of reasons for the minimum greenhouse gas reduction. You have the additional renewable electricity generation. It's important to have additional renewable energy stations, and you need to make sure that it's not just a new mix. The concerned consumers take the good electricity, and the ones that are not interested get the gray ones. So it'd be a change in the mix in overall. And also, it's important to think of the perspective that you have the production of power to gas, power to liquid in North Africa or the Middle East, and it can't be the case that the energy transition there gets slowed down by the usage of the electricity, the greener electricity produced there for fuels that go to Western Europe, for example. Then we have CO2 from sustainable atmospheric sources. We say that only CO2 capture from the air or sustainable biogenic sources create a closed carbon-neutral CO2 cycle. If this cannot be achieved, all CO2 emissions are to be counted. Well, what is the reason that we say this and say it's not a good idea to use CO2 from, for example, the cement industry or the steel production? We think there should be not even such a transitional phase, because we need investments in the key technology for climate neutral power to gas and power to liquid. And if you look at the price differences for CO2 from those industries or from direct air capture, it's a big difference. I brought the numbers here. You have for direct air capture for power to gas today 145, 100 more or less in 2030, and from the cement industry in Germany it's 30 euro per ton CO2 right now. So it's a big difference, and there won't be that pressure on investments in direct air capture that you would see if you don't use recycled CO2, so to say. There are various other options why CO2 shouldn't be used from those areas, but this might be then a part of the discussion afterwards. We have further on sustainable use of water and land. That should be obvious, and we have social sustainability of fuel production, so that the country where the fuel is produced keep some main sustainability aspects. And what we say is that the portion, for example, of the revenues must go towards sustainable local development. I wanna keep it like that, and I have some time for discussion. But I wanna at the end show our conclusions drawn at a glance. Synthetic fuels will play an important role in decarbonizing the chemical sectors, the industrial sector, and parts of the transport sector. Second, to be economically efficient, power to gas and power to liquid facilities require inexpensive renewable electricity and high full load hours. So excess renewable power will not be enough to cover the power demands of synthetic fuel production. Third, in the beginning, synthetic methane and oil will cost between 20 and 30 cents per kilowatt hour in Europe. costs can fall to 10 cents per kilowatt hour by 2050 if global power to gas and power to liquid capacity reaches around 100 gigawatts. Matthias explained that. So, and the fourth point, we need a political consensus on the future of oil and gas that commits to the phase out of fossil fuels, prioritizes efficient replacement technologies, introduces sustainability regulations, and creates incentives for synthetic fuel production. That's our conclusions at a glance. And thank you very much for listening under these complicated conditions here. And we look forward to your questions. Thank you. Okay. So, Christoph Graf says, "Hi guys, is there a use case where it is more profitable to produce?" Now it's gone. Is there use
to produce heat instead of gas or liquids?
Okay. Well, is there?
Sorry.
Different conditions, complicated. May I use the mouse, please, Christoph? Okay. So we have Leonard Push from Evomum. Which requirements does the water need to fulfill? And it needs to be desalinated water, needs to be fresh water. So to have such a plant in northern Africa, so to for example, you need a desalination plant where you get fresh water. Christoph Graf, that's the question I was gonna read before it somehow vanished from our computer here. Hi guys, is there a use case where it is more profitable to produce heat instead of gas or liquids? How could that case look like? And I would actually like to hand that over to Matthias.
Well, yeah, thank you. Interesting question. There's nothing that comes to my mind directly. The point is that gas or liquids just have a very high energy quality. I can, as far as I understand it, I can always derive some kind of heat from gas or liquids, and therefore it is such a high quality that for me it's hard to see this case where it's more profitable. That will be my first impression. Therefore I can't give you such a case, because the one can always be derived from the other. So let's jump to the next one. Stefan Schönberger asks, why is synthetic methane equally expensive as synthetic liquids, for example kerosene? Good question. We were also surprised when we got the results. I encourage you to look at this interactive Excel spreadsheet calculator that we put online, also in English and in German. The point is that there are two components, and in one case it's less expensive, and in the other case it's a bit more expensive. So gas and liquids kind of it's very close together in the range of cost, because those two components just cancel each other out, and therefore those two cost ranges overlap. I cannot give you more details at this point here, but if you have more questions, drop me an email and we can look at that together. But it's just about two components that cancel each other out. Other than that, I understand your question well. That's it's surprising at first. So there's somebody without a name. So one thing to consider would be checking the assumptions of frontier economics on the power to gas and especially power to liquid costs, which may be too optimistic. Yes, Absolutely. I encourage you to check those assumptions. That's exactly why we provide the spreadsheet and the interactive calculator. If you come to the conclusion that there's something you don't buy, then please contact us. That's definitely interesting. What you get from the study is that Frontier took a whole range of studies for investment costs and other cost components to build a kind of, we think, a very robust case, and then come up with the cost ranges. And again, those are cost ranges, and I mostly referred to the kind of middle reference cost, but we certainly understand that the ranges are much lower and higher and have something that is different from the numbers that we quoted when we said 20 to 30 cents and 10 cents. That's a simplification. They are cost ranges. Markus Ostermeier asks, CO2 from direct air capture is very expensive. Have you taken CO2 from biogas into consideration? CO2 from biogas should be for free. So that part of the question, no. We tried to develop a vision for synthetic fuels that looks at large volumes in the long run for deep decarbonization. Yes, biogas makes sense, and for certain pathways and for certain volumes it will certainly be part of the solution, but that was not our ambition. Our ambition was to look at the large volumes and long-run climate neutrality, and that's why we only looked at direct air capture. What you find in our spreadsheet tool, though, is you have the option to include CO2 emissions from the cement industry. I understand that that's not the same as biogas, but at least you can play around to see how a less expensive CO2 cost play out in the calculation. So there's a second part of the question asking by Markus Ostermeier, for electrolysis, water is necessary. Producing power to gas, power to liquid in the desert could be a problem. Has this been taken into consideration? Water is part of the cost calculation. What you find in the calculation, again, in the spreadsheet tool, is water is a minor cost component. This is something that I've talked to people in the industry. Let's say a large German supplier of components has said yes, that is consistent with their understanding and their estimate how kind of inexpensive water in the desert would be. Again, please scrutinize our assumptions wherever you can. This is our state of knowledge, but that's exactly why we put this online, to scrutinize this and to bring forward the discussion and provide transparency. Assuming costs, next part of the question by last part by Markus Ostermeier, assuming costs of 150 euros per ton for CO2 makes the methane very expensive. Especially for a start, biogenic CO2 could be used, and this should be available for free. This is more or less the same question that I had on biogas. Yes, but again, we have tried to paint a broad picture for the future large volumes. We have not so much focused on what could be the best, most inexpensive start, but rather what's the solution in the long run with large volumes. Yeah, so I'm aware that we are approaching the 5 p.m. Can we extend the time a little bit? So our chief technical advisor here says we could kind of go a bit further than just 5 p.m. So let's add another 10 minutes, I would say. That should be appropriate here. So Carlos Arruego is asking, what's the level of CO2 prices required? We have not assessed the level of CO2 prices required. What you find instead is, and the reason is the following. There has been a long discussion on higher CO2 prices in the European Emission Trading System, ETS, and the usual defense line of some industries is, whoa, we cannot afford to have such high CO2 prices. So our understanding is, even though it would be economically advantageous to have a high common CO2 price, that is not going to happen anytime soon, and therefore we have rather added our conclusion that we think it's rather likely to have an additional instrument. In this case, it could be something like a quota that incentivizes green or renewable gas or liquids in the system, instead of just waiting for a CO2 price that is high enough, which may be a long time to wait. Second part by Carlos Arruego is the question. In the slide 20, you mentioned additional renewable electricity generation using guarantees of origin, for example, imported from hydro in Norway. Would it be a valid option? Guarantees of origin imported from hydro in Norway. Well, if something is already there, like many imported hydro plants in Norway, it's obviously not additional in our sense if we want to have kind of additional renewables to decarbonize, especially the heat and transport sector. So I cannot really imagine something that's already there now to count as additional renewables.
I could add on that. Very good question. Thank you very much for that. We have a perspective where we look, for the reasons Matthias explained, at huge production sites, where you have very good places to have wind power and PV power, and where you need access to the water desalination plant and so on. If you think of smaller plants in Germany, for example, it is of course more complicated to have additional renewable electricity generated with no connection to the grid, as we say it here. Guarantees of origins would be a solution for that. However, what we want to make sure is that there really is this really is additional to the energy mix we have so far, and discussions about that are then, for example, following the line that there are some windmills in Germany in northern parts where the feed-in system doesn't. It's just run out, and you have that windmill, and you could use it for such a plant. And it has been financed by the public, by the electricity users. To make sure that it is additional, we think it is best to have actually no connection to the grid. Guarantees of origin would mean a connection to the grid, and it would mean an exchange of electricity quantities. What is the next question, for example, is on slide 15. What is the share of total cost coming from carbon capture? We don't have it here with us in this room. It was prepared with extra slides we had in the original system. But yeah, Matthias is looking it up actually. I'll go for the next questions. Well, then we'll change again.
Sorry for the technology here. You, again, as I say, you can always try to look up those cost answers in our Excel spreadsheet tool. What you find on page 84 of the report is the following phrase: the costs of capturing CO2 from the air make up about 10 to 15% of the total costs of methane production. 10 to 15%. And also, as I said before, seawater desalination is negligible. So those are two cost components that are, of course, under discussion, but they don't make a big component here in our calculations. But again, look that up in the calculator. There's another question. What is the hydrogen based on? And I think this question refers to the slide where we compare hydrogen with methane, because that is the only hydrogen cost that we really had here in our presentation. And the question is, does it come from the Baltic wind or PV in Africa? And on the slide you can see that in the footnote it should say the hydrogen and the methane are both produced based on PV in, I think it's North Africa. It's in the footnote, and so that's one example calculation. And the core message is the hydrogen is about 50% the production cost of the methane. We already had that question on heat, so we skipped that one. That was one of our first questions. Then we move on to Julien Pestiot, who's asking, why is electric batteries in shipping not feasible? Ships can easily handle, can easily carry very high loads. I put this over to
there are actually ships that use batteries, but only for shorter distances. And if you think of container ships going from Asia to Europe, there is no case that you use the ability to carry weight for the batteries and so much less for the goods you want to transport, you want to ship. So there will certainly be more ships using batteries. There are some hybrid concepts already on the waters. For example, those ships that those boats that I don't know the English term, but help other boats that are approaching harbors to find the right place in that harbor, and so and for maintenance some boats. So it is definitely an option, and there will be more electric batteries. I want to use that that opportunity to say that. For example, in Norway, it was announced by some airport operator to have short distance flights with battery electric planes. There was also EasyJet that said they want to have short distance battery electric flights. Whatever that, how realistic that is, it might be a very efficient way to use planes, but looking at longer distances, that is certainly not very likely to have that in the next decades. So the next question by Frank Brüning: how high is the current market price for methane at the moment, and how high is it if you make it from electrolysis at the moment? We would have to. You know.
The one thing is that I wanted to add is that we are approaching, unfortunately, the end of the session. We take this question and then see, but I'm just saying that we cannot do this much longer. So the current market price for methane at the moment, well, the question of cost and prices. So we have looked at cost here. And one thing that you get from the slide with the cost where we present the overview is that we really start by 2022. That's not today, and I acknowledge that. It's for the simple reason that we think we're talking about those huge plants that need to be constructed, and you need to build them. So we cannot talk about the cost today, because really, if you want to provide relatively inexpensive methane from North Africa, that will take some years to construct large chemical factories there, and therefore we have started with 2022 because we think that's a reasonable time period, and then you can see that 2022 would be something like 18 cents is the reference cost, and fossil methane cost and natural gas is more like 2 to 3, rather 2 cents, and it's a big gap, and therefore we think the market by itself will not provide synthetic fuels. Maybe one more question here. I think then we are approaching, unfortunately, the end. Steffen Eppler from Bosch asks, which incentives for synthetic fuel production do you have explicitly in mind? Who should pay the learning curve, which application? I think let me try to answer this in a broad way. So the incentives for synthetic fuel production, we have explicitly in mind that there could be something like a quota, and it means the quota in a broad sense would mean there's a requirement for someone, be it the one who's, for example, selling natural gas today, or the one maybe operating the grid, but someone has the obligation to bring in a certain percentage of renewable gas or power to gas into the system, and then he or she will certainly try to take that cost and put the cost over to his or her customers. So in the end, the fossil fuels will increase because there's an obligation to have a certain percentage, a certain increasing percentage, increasing over time, of blending more and more synthetic fuels, more green fuels into the product. That's kind of the level of abstraction that we have discussed so far. There could be another arrangement, but we think in the end it's kind of the cost, the basis of those who pay for it should be those who are paying for the fossil fuels. So we think designing an incentive should be then financed by those who are today consuming fossil fuels. That means in the end fossils would increase due to an obligation to blend in power to gas, power to liquid. So that's at that level of abstraction, I think we can answer this here. And final question, who should pay the learning curve? Well, we think it will be expensive. It will be incredible investment into the learning of electrolyzers and some other components, CO2, direct air capture. So this is what we call a global 100 gigawatts challenge. We don't see that a country like, for example, Germany alone would pay for all those electrolyzers, because it's a global challenge and a global learning curve. And once costs have fallen here, remember the story of PV. They will fall all over the planet at some time, and then we will all benefit from that. And therefore it's a global challenge and a global obligation to get the cost down there. Thank you very much. I think at this point we're saying thank you for listening, thank you for asking. Again, there are some open questions here. We're sorry for that and for the technical delay, but we still have those questions. As long as we have your email, we can kind of try to answer them bilaterally.
You mentioned the newsletters. Well, then a very important note at the very end. I just wanted to mention that we have newsletters on our websites, Agora Energiewende, Agora Verkehrswende. We won't spam you with mailings, but it's an option for you to keep up to date on our activities. And yeah, as said, we want to follow up on the questions that are left. And just from my side, thank you very much for your interest and for your active participation. And yeah, under those a bit more complicated circumstances, and it's a good opportunity to say thank you to Christoph and Nicola, who yeah, stayed calm when the computer just started turning off. So thank you too, and see you next time.